Today we're talking about fungi. No, not me after a bottle of wine, as in yeast, Candida. If you know or think you have an issue with chronic fungal problems, and all those antimicrobials like oregano oil, etc., aren't giving you a long-term solution, then this video is for you. Now, for our purposes here, fungi, yeast, and Candida are pretty much one and the same. The kingdom fungi is a huge grouping of living things with a nucleus, such as mushrooms, molds, and yeasts. Yeasts are fungi. And Candida is a type of yeast, in other words, a form of fungus. Candida albicans is the most notorious species within the genus Candida, and although there are other species, we'll mostly focus on it. You have to realize one important thing as we begin. The fungi/yeast within you are, to a large degree, a normal part of your microbiome, but are in essence opportunistic pathogens waiting for their chance. This is the same principle I cover all the time when talking about bacterial opportunistic pathogens. If you give them an inch, they may take a mile, and your health could suffer. If you're new, be sure to subscribe to my YouTube channel and also follow me on Instagram and Facebook as The Microbiome Expert. Now, if you've tried killing off yeast in the past, whether it be with natural products from garlic, berberine, oregano, etc., or with drugs, you have to realize you're not going to kill all of the yeast in your body. They will hide out in reservoirs waiting for their opportunity. We have to leave behind this kill, kill, kill mentality and support you via the environment of the microbiome and your immune system. This paper talks about drug resistance, which is common with Candida. Candida has a pretty quick workaround for the drugs. If you've taken fluconazole or nystatin in the past, it probably worked well the first few times. But if you're still taking them after a number of rounds, guess what? You're likely going to be spinning your wheels. So we're going to need another strategy. Feel free to read this relevant content from this paper. And you're welcome to get the whole paper and read it for yourself, just like any other paper I highlight. So let's take a step back to better understand our opportunistic enemy. Of the estimated 1.5 to 5.1 million species of fungi on Earth, only about 400 are known to cause disease in humans. But most all are not inhabitants within us. Looking at just the gut fungi, many of them are incapable of colonization or long-term persistence in the gut. Candida albicans is one of the most, if not the most prevalent, commensal fungi species of the human microbiota, asymptomatically colonizing numerous body sites, including the GI tract, genitourinary tract, and skin of healthy individuals. Of the more than 150 species of Candida, approximately 20 are known to cause infections in humans, C. albicans being the most prominent. But how does it go from being a harmless commensal to potentially deadly? Because you let it. You gave it the opportunity to become a pathogen, hence the name opportunistic pathogen, and hence the title of this paper, Candida albicans and the main opportunistic pathogenic fungus in humans. You can see from figure 1 the yeast form, where C. albicans can travel more efficiently, and the more pathogenic form to the right. We see more of this here from the same paper, where the arrows are pointed to the pathogenic hyphae, which we'll talk about in a minute. You need to understand how nasty the species from Candida can be. Infections caused by Candida species are responsible for the majority of the reported global deaths by fungi. In the USA alone, it was reported that sepsis caused by C. albicans has a mortality rate of approximately 40%, which is higher than any other sepsis caused by bacteria or fungi. Infections caused by the genus Candida are the main cause of nosocomial, hospital-based, fungal infections. Candida species of human fungal pathogens are a significant medical problem because they can disseminate to nearly every organ of the body, including the brain, kidney, liver, lung, and so forth. Now, for those of you watching this video, the vast majority are not worried about sepsis from Candida, but you need to understand the principles of how one gets there. So here we see the life cycles from those little spheres to the elongated, branched-looking thing called hyphae plural. And here you can read about how antibiotics, dysbiosis, and immune dysfunction are the main risk factors behind Candida being a harmless commensal to a pathogen. Just like with the bacteria I'm always talking about, when given the opportunity, the bad bacteria and Candida act no differently. They will take advantage of a situation, which is why philosophically I don't view yeast any differently than I do bacteria. And speaking of bacteria, they are the most abundant organism in the gastrointestinal tract. More than 99% of the genes in the human gut microbiome are of bacterial origin. Less than 1% is fungal in origin, which is why I say when you control the bacteria, you control the microbiome. But when the microbiome is dysbiotic, unhealthy, that 99% controlled by bacteria is largely influenced by bad bacteria. And that less than 1% that is fungal can become quite pathogenic. The bad actors, whether they be bacteria or fungi, thrive in the same conditions as you will see. The conditions that I always discuss. And they are kept in check by the same mechanisms I always highlight. From this paper, we have this great illustration, which is also scary as hell. We see the epithelial cells, which are the first line of defense, along with mucus, which we'll also touch on later. These cells induce the expression of various antimicrobial peptides, which control C. albicans growth in the commensal phase and during infection. In addition, the tight junctions seal the space between the host cell surface and the mucosal lamina propria, thus preventing interepithelial invasion by C. albicans. So we're talking gut permeability here. For much more, see my video. Like we said earlier, the Candida can travel as those spherical buds. Then, if given the opportunity, pass through the cells that line your gut by various mechanisms, being gobbled up by immune components, passing in between the cells, passing through where entire cells had died due to damage, or, as we see in D, boring right on through and then switching back to buds able to travel systemically. So if the gut is the reservoir for systemic infection, then we need to do our best to control Candida via the health of the gut microbiome. Again, yeasts are much like bacteria in many ways. For example, I talk about how if bad bacteria are given the chance, they will adhere to and invade the cells that line the gut. Well, Candida is no different, as you can see here. Contact to host cells triggers the yeast to hypha transition and directed growth. In probably every paper you'll read, there is mention of how the hypha stage is the most nefarious. Following adhesion to host cell surfaces, C. albicans hyphae can secrete hydrolases, which have been proposed to facilitate active penetration into these cells. In addition, secreted hydrolases are thought to enhance the efficiency of extracellular nutrient acquisition. 3 different classes of secreted hydrolases are expressed by C. albicans: proteases, phospholipases, and lipases. One of the key nutrients C. albican needs is iron. C. albicans acquires iron by different strategies, including a reductive system, a siderophore uptake system, and a heme iron uptake system. The reductive system steals iron from your ferritin or transferritin, or it can steal it from the environment, such as with iron supplements. The heme iron uptake system promotes iron acquisition from hemoglobin and heme proteins. The last mechanism was called the siderophore uptake system. If you're familiar with my videos, you may recall me mentioning siderophores previously, like in the video here, on emotional stress in the microbiome. Bad bacteria also have a way of stealing iron from you. Siderophores are extracellular ferric chelators, and their role is to deliver liberated iron to the bacterium. Bad actors love iron. When healthy, your body does a pretty good job of keeping iron away from them. But when compromised, these pathogens have an easier time getting their little hands on it, which is good news for them, but not for you. Now, Although C. albicans does not synthesize its own siderophores, the fungus uses an uptake system to steal iron from siderophores produced by other microorganisms, the bad bacteria. So you can see how misery loves company in the dysbiotic microbiome. Another thing bacteria and yeast share in common is the ability to form biofilms. The development of C. albicans biofilm occurs progressively and is typically classified into 4 stages. 1. Adsorption and adhesion of C. albicans yeast cells to a substrate. 2. Formation of microcolonies and production of extracellular matrix. 3. Maturation. And 4. Dispersal of cells from the mature biofilm. Once established, C. albicans biofilms are highly tolerant to antifungal therapy and can serve as a reservoir for recurrent infection. Do you think your oregano oil is going to resolve this? The drugs can't even do this. Instead, let's control the environment so when the buds are released from the biofilms, they and their potential hyphoform is kept in check. Part of that environment is controlling for lactate. I mentioned this concept in many videos to include these 2. I discuss how the dysbiotic environment is typically a high lactate environment. This in part explains why the so-called probiotics from the genus Lactobacillus are a bad idea, and why Lactobacillus species are almost always higher in the unhealthy microbiome versus that of the healthy controls. I have many videos on this topic. And in this paper, these authors go on to state, quote, "This suggests that depending upon the host niche, C. albicans has evolved to exploit either of 2 host signals, hypoxia or lactate, to promote immune evasion." Another key factor in common for both pathogenic bacteria and yeasts are their thirst for components of mucus. I talk about this extensively in my video on opportunistic pathogens, where in this video I highlight how bad bacteria key in on sialic acid as a signaling molecule to grow. Among other things, mucus and HMOs for that matter are primarily composed of sialic acid, fucose, and something called N-acetylglucosamine, which is an amino sugar, which is an important component of bacterial cell wall peptidoglycan and fungal cell wall chitin. In fact, it is so important to C. albicans that it completely keys in on its availability. You can read here, or I can put it in more simple terms. When C. albicans recognized N-acetylglucosamine in a medium, it cranked up its machinery. But this medium only had N-acetylglucosamine, no other supportive nutrients. The internal machinery was so cranked up that C. albicans shortly died from a lack of other building blocks. I often mention signals in my videos. Signals are at the key to so many processes in the body. The signal here is that of a compromised mucus layer. Bad bugs, whether they be bacteria or fungi, need molecular signals to tell them to go wild and do bad things. They don't have eyes and ears like we do, obviously, and so have to have these intricate signals built in. What better signal than when a nutrient-rich source, first line of defense like mucus, becomes compromised? I hope you're enjoying the video so far. Don't forget to like, subscribe, and recommend to friends and family. Also, if you're feeling extra generous, hit the super thanks below. And for something I always am mentioning, guess what? pH also plays a role in the virulence of Candida. I have an important video dedicated to this topic. Again, we're talking about the importance of signaling, this time done by something called RIM 101. And as the quote says here, this is an important regulator of the yeast to hyphae transition. And we already know how important those intracellular boring, tissue-destroying secretors are to Candida virulence. And here, you can see our compound, N-acetylglucosamine, whose catabolism increases the extracellular pH. It becomes more basic, which favors the hyphal growth, the nefarious stage of the Candida life cycle, via the RIM 101 pathway. And from this paper, which has the interesting title of From Jekyll to Hyde, the Yeast Hyphal Transition of Candida albicans, we see, among other factors, a pH of 7 being an integral part of this transition. We don't want a pH of 7 in the gut. This is where the bad actors can outcompete the good guys. We want our pH in the Goldilocks zone, one which favors the health-promoting, antibiotic-sensitive butyrate producers. When they produce butyrate, propionate, and even acetate, the pH drops to something that is slightly acidic. This is one way in which we control the environment. To further enforce this point, these authors go on to state, quote, "One striking feature that allows C. albicans to cross the commensal to pathogen boundary is its ability to switch reversibly between two morphological forms, namely unicellular budding yeast to filamentous form," that's the hyphae form, in response to various environmental cues that reflect the host environment. Environmental cues, signals, which reflect the host environment, such as antimicrobial defenses, gut barrier integrity, bile acid metabolism, mucus integrity, and of course, pH. Continuing on the theme of pH, I want to transition to vaginal health. It is estimated that approximately 75% of all women suffer at least once in their lifetime from vulvovaginal candidiasis, with 40 to 50% experiencing at least one additional episode of infection. A small percentage of women, 5 to 8%, suffer from at least 4 recurrent cases per year. Predisposing factors include diabetes, use of antibiotics, oral contraception, pregnancy, and hormone therapy. In Table 1, you can see vaginal bacterial communities clustered into 5 groups. The lowest pH, that dominated by the species Lactobacillus crispatus, is repeatedly shown in studies to be the healthiest. For much more on this, you can watch this video. So, although I do not recommend Lactobacillus in any form for gut health, when it comes to vaginal health, it's a different story. But with that said, my philosophy is still to address gut health. But why? When you address the gut microbiome, you address the bacterial reservoir and its ability to translocate, move from one location to another. This is true in UTIs, which you can learn about in this video, and it's true for vaginal health. And a huge risk factor for vulvovaginal candidiasis is antibiotic use, as highlighted here. And antibiotics kill all bacteria, both good and bad. But the good guys tend to get hit harder, and the bad guys recover faster and stronger. You can learn more about that in this important video. So, as a part of this collateral damage, the health-promoting bacteria in the vagina, like L. crispatus, tend to get killed off or at least sidelined. Like in the gut, this is where the not-so-health-promoting occupants take over. This is why women who have had many rounds of antibiotics tend to have chronic yeast infections. I have seen a number of these women, some of whom who have had more than 100 rounds of antibiotics in their lives. And yet, by addressing the gut microbiome, I was able to improve their vaginal health dramatically for the better. Additionally, occurrences associated with high estrogen, such as oral contraceptives, pregnancy, and hormone replacement therapy, have been described to predispose to vulvovaginal candidiasis as well. This slide comes from my videos on autoimmune disease, where I talk about how females in general have a higher prevalence of autoimmune disease after adolescence, and that various studies show that women have more intestinal permeability than men. So these researchers took things a step further and looked at the cells that line the gut of both men and women. So what did they find? They found that women had significantly lower zonular occludens, ZO levels, as compared to males. I've mentioned zonular occludens before. It's a key component which holds the enterocytes together to avoid intestinal permeability. They also showed that estrogen inhibited ZO1 mRNA and protein expression in human primary gut tissues. Permeability is not just a gut concern. We have a tremendous number of cells held together by these connections, to include the cells that line the vagina. Now, if you recall back to the beginning of this video, I talked about how Candida is a normal member of the microbiome, and if kept in check, is not pathogenic, but given an opportunity, it will become opportunistic. We also talked about controlling the environment with a sound mucus layer, cellular integrity, and pH as important factors, all of which are in large part controlled by a healthy microbiome. There are other controls. We talked about how antimicrobial peptides were a part of the first-line defense. Well, here we have the most important gut immunoglobulin antibody, IgA. To learn much more about IgA, watch this video. IgA plays a key role in controlling Candida. Think of IgA as your own personal diflucan or nystatin, but without the drug resistance. IgA is a huge player in the gut immune system. And remember, it's the immunocompromised who oftentimes go on to suffer and possibly die from Candida sepsis. These researchers state, quote, "Here we investigate the role of adaptive immunity in promoting mutual interactions between fungi and host. We find that potentially pathogenic Candida species induce and are targeted by intestinal immunoglobulin A responses. Focused studies on Candida albicans reveal that the pathogenic hyphal morphotype, which is specialized for adhesion and invasion, is preferentially targeted and suppressed by intestinal IgA responses. IgA from mice and humans directly targets hyphal-enriched cell surface adhesions. Another way to control Candida is through bile acids. Now, most people with dysbiosis of the gut microbiome will also have some level of bile acid dysmetabolism. And bile acids impact the microbiome, and the microbiome impacts the bile acids. I talk about bile acids often, but I take deeper dives into this topic, especially in these two videos. In this paper before us, we see in A and B that the secondary bile acids, LCA and DCA, inhibited C. albicans growth in vitro. Additionally, as shown here in a different A and B, they also significantly inhibited the germ tube, hyphae, and biofilm formation in C. albicans. An altering of bile acids is critically important for the microbiome. This is how C. diff is able to be highly pathogenic and kill some people, while for the rest of us, we have no symptoms. It's the cycle of antibiotics, the killing off of butyrate producers, dysbiosis, the resultant inflammation, gut permeability, and bile acid dysmetabolism, which is at the root cause of not only C. diff, but everything I talk about. It's all connected. So if you want to end the chronic cycle of yeast problems, then you really need to address the whole environment. In summary, let's look at a few quotes from this paper which simply reinforce everything we've covered here, and in reality, in my videos in general. These are knowns. This stuff isn't a mystery to me. But in a world of broken conventional medicine, biochemistry and data get thrown out the window for profits. Your practitioner probably does not know what I know, and what these researchers know when they say, quote, "The evidence is overwhelming that C. albicans in the GI tract is a major source of systemic candidiasis, and numerous experimental models have revealed that this fungus can enter the bloodstream by translocating through the intestinal barrier." End quote. It seems clear, however, that in humans the bacterial microbiome plays an essential role in controlling the level of C. albicans colonization, since the use of broad-spectrum antibiotics is recognized as a major risk factor for candidemia. End quote. The picture that emerges is that C. albicans is well adapted to growth without glucose. Remarkably, changing environmental conditions, such as the availability of carbon sources, e.g. lactate instead of glucose, impacts fungal adaptation, which can influence colonization and pathogenicity. End quote. However, antibiotic treatment prevents the conversion of primary into secondary bile acids by commensal bacteria. The consequent accumulation of primary bile acids, such as taurocholic acid, can increase C. albicans outgrowth and stimulate filamentation. My hope was that this video gives you some insight into chronic yeast infections. you need to realize that by taking some antimicrobials, which everyone does, and by cutting down on sugar intake, that the odds are you're not going to have a long-term solution. If you've been going in circles, either through your own research or working with multiple practitioners, maybe it's time to try something more intelligent. If you reflect back on what you learned in this video and think to yourself, there was a bunch of information here I didn't even know about before, then perhaps it's time to reach out to me. My philosophy is different. I don't focus on bug killing. You're not going to get all of them. I focus on you and your ability to be strong and keep these omnipresent, opportunistic pathogens in their place. They are looking to take advantage of you when you're weak. I want you to be strong. In order to do that, we need to correct the hits you and your microbiome have taken over the years, such as excessive antibiotic use. So let's get you started. Check out my new yeast/candida protocols. If you liked the video, don't forget to subscribe. Also, somewhere around here, you can go to my website where you can schedule a consultation with me. You can also view the protocols, and here you can watch the next video.